Hello and welcome to video number 3 of me, old man, trying to relearn Maxwell's equations. Okay, we're still in chapter 1, but now we're into the differential form of Gauss's law, which is the del operator inner product with the electric field is equal to the density divided by the permittivity of free space. Okay, the del operator is defined in Cartesian the coordinates as this. So it is the orthonormal basis of vectors, the product with the partial derivatives in whatever the coordinate system that you have. In this case, this is the Cartesian one. But the del operator acts like this. So it is an operator that's acting on something. And in this case, it's acting on a vector, the field, which has these components. These are not the format I would have chosen, but it's his book and he's the boss. Acting on these components with these basis vectors, right? And x hat dot x hat, remember, is 1. X hat dot y hat is 0. So all the cross terms are gone. So you're just left with this. So this is called the divergence of vector field A, is the way you read this. Now, the very first problem in this section is you need this in spherical coordinates. This is in Cartesian the coordinates, and he gives you the equation, but I'm not happy with just seeing it. I said, well, where does that come from? I want to know what that is. I want to know how to derive that. Whew, be careful what you ask for. It's a lot of work. Let's get rocking. Okay, so we need to do some transforms. The first thing we're going to pick is transforming these partials into spherical coordinates, okay? So in tensor calculus, we would write it like this. We would say the unprimed the system is changed to the primed the system via this Jacobian. And you notice that I have the free index I in the lower position, free index I in the lower position. That makes these two primed indexes the summation indexes. All right, so as an example, we would write the partial derivative of x, and that's our free index, and it's here, so we have to use it in the same place every time, x, x, x. This becomes our summation index. So we have 3 dimensions because we're going to from xyz to r theta phi. So in the first case, it's r. The second case is theta. And the third case, it's phi. So in vector calculus, you would call this the multivariable chain rule. It's the same expression as this, but this is the way we prefer it in tensor calculus, which is my favorite subject, by the way. I think I've mentioned that. So you have to write all 3 of them out like this, right? So now, in order to solve this, we have to find each one of these partial derivatives to go into these equations. And that's not a lot of fun, but it works. So here's the transpose equations you need, right? So you've got r theta phi. You're going to use these in this part, and then you're going to use these transposes from xyz to r theta phi, the inverse of this, to simplify them. All right. So let's get rocking. Here's an example. So what is the partial derivative of r, this, with respect to x? Well, it's x over this. That one even I could do. All right. So now you see x is this. So you put that in to simplify it. And this is just r. See? So you put that in and it simplifies to that. Now this one was not easy. And I went to an online math calculator to do these. I'm not doing this by hand. I don't even know if I could. Anyway, here's what you get. You plug in all of these guys, and it simplifies to this. Now, there's pages and pages and pages of algebra here, so I don't really think that's the point. So I'm going to not show that because it's too much. I would be stuttering for 2 hours, and nobody wants to hear that. Okay, so the last one is the phi with respect to x. It simplifies to through this. All right. Now I'm just going to write all the rest of them out like this. So here is now we have these partial derivatives with as a function of the derivatives of r, theta, and phi. All right. So what's the next thing we need to do? Well, we did this part. Now we need to find these components of this vector, arbitrary vector, as a function of r, theta, and phi. Well, how do we do that? The same way. Use the Jacobian, baby. All right, so here's his format now. This is not mine. This is his, but he's the boss. So we have a unprimed and primed the coordinate the system. So this is a vector component. This is my free index. So I have to put it here in the bottom, just like this. And then my primed is the one I'm going to. So this becomes my summation index. So I write out each one of these like this. So in the first case, it's x. So I go through and go, because we have 3 dimensions, x, x, x. This is my summation index, r, theta, and phi, okay? And the Jacobian means the partial of r with respect to x, the partial of theta with respect to x, partial of phi with respect to x, all right? So we did all these already. We have them up there above. So we fill them in, we get this. Now what do? Well, now we have this piece and this piece. We have all 6 the pieces. We have to put them together like this. Here's an example. So this one term here would be, this is the partial with respect to x in terms of r, theta, phi. And here's the ax component in terms of r, theta, phi. We multiply all that out. We simplify it. And we get this. So finally, this reads as the divergence of the vector field A in the coordinates. Okay? So now that we have this, we can do our first, the problem. Okay, and here's the problem in the section on the Gauss's law and derivative of the form. Find the divergence of a field given by vector A is equal to 1 over r in r hat in spherical the coordinates. Okay, so here's the mess that we went through to come up with this, right? So you see that there's only one part of this that has anything to do with r, which is the first part, okay? Because the partial of this with respect to theta or phi is just the 0. So I put that in. I got 1 over r here, r squared there, takes 1 out. The partial derivative of r is just 1, so I got 1 over r squared. So it's kind of anticlimactic considering what we went through to get this equation here. But I thought this was actually fun to do. It took hours. It took hours to do it. I made a lot of mistakes. But it's fun to sit down and do if you have time. All right, I'll see you on the next one.